Hello everyone and welcome to .NET Core Central. In today's video, I'm going to talk about the process of garbage collection. Now, garbage collection is something we as .NET developer take it for granted. But if you have worked on C or C++, some of the unmanaged languages, you know how hard it is to manage object lifecycle and manage memories and how to collect garbage. Managed frameworks like .NET or Java makes it really simple for developers. And in today's video, I am going to talk about details of garbage collection in .NET. This is true for both .NET Framework as well as .NET Core or .NET 5, whereas some of the inner workings might be a little bit different between .NET Core versus the legacy .NET Framework. Now let's talk about what is garbage collection. Garbage collection is the process of cleaning up unused memory inside of a .NET process or a .NET running application. The CLR or the Common Language Runtime allocates memory into managed heap when an object is created, and when the object is not used anymore, that's when the garbage collector goes and reclaims the memory. Managed heap something is an interesting topic, and I'm going to talk in detail about it in the next couple of slides. Since memory is a finite resource, hence it needs to be freed up at some point in time based on the availability, and that is where the phenomenon of garbage collection happens. Next, let's talk a little bit about the garbage collector itself. So the garbage collector is a component inside of the CLR or the .NET Framework that is responsible for automatic memory management. By automatic memory management, I mean it takes care of both allocating as well as deallocating memory inside of the CLR. Now let's talk about what are some of the benefits of having a garbage collector in a framework like .NET. First of all, the developer does not have to worry about managing memory themselves, which is a huge win. Memory allocation is very efficient because it is programmed and it is not individual developers' way of doing. It provides more safety in terms of making sure that one object cannot use content of another. And finally, it finds out and cleans unused memory automatically. So these are few of the very basic advantages or benefit of using a garbage collector. Next thing I'm going to talk about is the managed heap. Let's understand what is managed heap. The CLR does memory allocation in a contiguous memory space of the process, which is known as the managed heap. Now CLR uses the lower level operating system method to get a portion of the physical memory, and then it uses that memory as managed heap to manage all the objects which will be created as a part of the .NET process. The managed heap always contains the address of the next available location where the next object will be allocated. Every instance of a reference type created are saved inside of the managed heap. And the next thing is all the threads that are created inside of a .NET process in the application allocates memory in the same managed heap. Meaning for a particular process, there is only single managed heap. There are no multiple managed heap for each thread. Every thread gets the same managed heap where it saves the object. Now managed heap has a very interesting concept called generation. So let's take a little bit of look into what are generations. Managed heap has three logical segments which are known as generations inside of the managed heap. The reasoning behind the generations are, first of all, it is faster to clean part of a managed heap instead of the complete heap. And when we talk about multiple generation, it will be clearer how this sentence is related to the generation inside of the .NET managed heap. Usually, the newly created objects have a shorter life compared to the older object, and that's where also generation helps. And newer objects are usually have similar lifetime and access during the same life cycle of a method. Now, these two sentences sentences need a little bit of clarification what they really mean. For example, when you are dealing with a web API, inside of a HTTP method, if you are creating set of objects, and if you drill down into the objects and inside that object you create 3 more, you can see the pattern that objects created together mostly have same lifetime. So let's say you are dealing with a get user method, and inside of the get user method you create 3 different classes: one for getting the data from the database, one for transforming the data that you got from the database, and third one is a class which is responsible for doing some validation. Now these 3 classes will be created inside of the same method, and usually their life cycle or their lifetime is over at the end of the method. So that was the last statement means. And the second statement, which says usually newly created objects are shorter life compared to old objects, is because if you take the same example, the 3 objects that are created will usually be short-lived and getting out of the memory cycle compared to older object. Talk about older object is if you consider you have a singleton class, that is an older object because it will be living throughout the life of the process. And there are of course other older objects that we can talk about. Now let's talk a little bit about the 3 generations in details. So the 3 generations are named as generation 0, generation 1 and generation 2. And apart from the 3 generations, we have another concept which I'll talk in the subsequent slides. Let's first talk about generation 0. This is the segment where the shortest lived objects are located, and garbage collector usually runs in this generation first. Next generation is the generation 1. This is the generation where objects are also shorter lived, but they are longer than compared to generation 0 object. When we get into details of how garbage collector works, this will become much more clearer. And this is kind of a bridge between the generation 0 and generation 2. And finally, we have the generation 2, and this is the generation which contains the long-lived object. For example, as I mentioned earlier, a singleton object created in a web API will usually end up getting into generation 2. In subsequent slide, we'll talk about how the promotion from one generation to another generation happens. Now, as I mentioned, apart from these 3 generations, there is another concept, and that is what we are going to discuss now. And that concept is called the large object heap, or LOH for short. So let's talk about what is large object heap. For performance improvement, larger objects are not kept in any of the 3 generations. It's because larger object will be harder to allocate as well as compact. Hence, it doesn't make sense keeping them as a part of the normal heap generations. Hence, they are kept as a separate location. It is called the large object heap. And as I mentioned, the large objects are kept in a separate location called large object heap. It is also sometimes called as generation 3. Objects that are greater than or equal to 85,000 bytes are moved into large object heap. According to the documentation, this number is determined by performance tuning. Now that we understand the concept of a garbage collector, what the garbage collection process is, and what is a managed heap, what are the 3 generations of heap and the large object heap, now let's get a little bit into details on how the garbage collector works. The first and foremost thing to remember is that the garbage collection is a non-deterministic method. The garbage collector usually determines when is the best time to run a collection. The garbage collector removes objects from memory which are no longer in use. It's find out if an object is no longer in use by determining the roots of the application. Now let's talk a little bit detail about what are the roots of an application. Following are the possible roots of an application. Static field, including singleton object. Objects that are created inside of main method. Variables created on a separate thread. Finalize queue, GC handles, and CPU register. Let's go through each one of them. I've given a star around finalize queue because it's a larger topic. It's need a little bit of time to discuss. GC handles and CPU register, these are the things we usually don't even deal with. So I'm not going to talk a lot of details about it. Let's talk about static field. Static fields or singleton objects usually will live throughout the life cycle of a process. Hence their root, meaning they will always be accessible. The object created inside main method is the same thing. If it is created inside main method and it is the entry point of an application, it will not be reclaimed or removed until unless the process is closed. Variable created inside separate thread. These are the variables which will leave as long as the thread is alive. Hence, it is also a root. Finalize queue is considered as a root because of how the whole finalizing process works. And as I mentioned, it's a whole thing to discuss. So I have a video about iDisposable. I am going to share the link above as well as in the description. But finalize queue essentially is something which is used by the CLR when a class implements a finalize method, which is also known as destructor in C#. Once a class uses a finalize method, what the CLR does is it keeps that object entry in a finalize queue, and it uses it to determine when the garbage collection should happen. Because if a finalize method is defined, that means the CLR needs to call the finalize method first, make sure all unmanaged resources are cleaned up, because finalize method is used for that purpose. If a class uses unmanaged method, then only it should be implementing iDisposable pattern, and as a part of the pattern, implement the finalize method. So the CLR first calls the finalize method during the first running process, and in the second time when it comes to run the GC, that's when it collects this object. So this is why finalize queue is also part of the root, and this is also one of the reasons that you have to be really cautious about using finalize. And that's why when you use finalize, you also use suppress finalize as a part of the dispose method. Again, you can go through my video to look into it a little bit in detail, but that's what it is. And GC handles and CPU registers are two other roots. And as I mentioned, I'm not going to get into the details. So now we understand what are the possible roots. Now let's talk about how the whole process works. Each of the objects in the managed heap are either null or they point to an object in the managed heap. These are the only two conditions they can have. Now, the way a garbage collector works is it creates a graph of object from all the roots. Why it is called graph of object? Because it's basically the objects which are linked to the root. So it is usually a tree structure where you have at the root level multiple objects, and then each object has reference to other objects internally, and that creates the graph. So how does garbage collector finds out objects needs to be collected? The object which is not a part of the graph but available in the managed heap are essentially the ones which are ready to be collected. If they are in managed heap, then they should be part of the graph. Otherwise, they are not being used anymore, which means they are ready for collected. The GC then calls the memory copying function of the operating system to compact the object which is still in the graph and move them closer to each other. And in the process, it frees up the memory. This operation will occur only if there are significant number of objects that need to be released. Otherwise, the compacting operation doesn't happen. It does release the object from the memory, but it doesn't compact if there is no significant improvement in the memory allocation. And then finally what the GC does, it adjusts the pointer to the next available location in the memory. Initially, before the fast garbage collection happen, the entire managed heap is considered as generation 0. At this point in time, there is no generation 1 or 2. Everything is generation 0. After the fast garbage collection and the memory compact process is done, the memory locations of the objects that survive the garbage collection process are marked as generation 1. So that is when fast generation 1 will be introduced after the fast garbage collection run. And whatever available space which are free in the managed heap are now marked as generation 0. And similarly, when the second garbage collection happens, the location of whatever objects that survive the generation 0 will now be marked as generation 1. But whatever objects from generation 1 survive the collection will now be marked as generation 2. This is how we get generation 0, generation 1 and generation 2. After the 3 generations are established, beyond that point, every collection will either move generation 0 objects into 1 and 1 into 2, or there is a possibility that all the objects in generation 0 are collected and generation 1 and 2 are not even touched. And there is also a possibility that some of the objects in generation 1 or generation 2 might be removed. Generation 0 and Generation 1 are also known as ephemeral generations due to the nature of the objects in these generations are short-lived. Now let's understand what are the different steps the garbage collector takes during the collection. So the garbage collector takes the following step during the collection process. First is called a marking phase. During the marking phase, it creates a list of objects that are still alive based on the accessibility from the roots. After that, it does a relocating process. In this process, it updates the reference of the objects which are compacted because it moves object around. Hence, it updates the reference. And the third phase, which is also called the compacting phase, this is the phase where it reclaims the address space of the dead objects and in the process moves the surviving objects towards the older end of the generation segment. Now, this is how the garbage collection happens on the managed heap Generation 0, Generation 1 and Generation 2. Similar garbage collection also happens in large object heap. But when garbage collection happens in large object heap, the heap is usually not compacted unlike the managed heap generations because the cost of compacting is much higher in a large object heap. So this is how the complete garbage collection process works. Now apart from this, there is another thing to remember is there is a method called gc.collect which can also be used to manually trigger a garbage collection. Again, this method does not guarantee a collection, but if a collection is happening when you call this method will return automatically. Otherwise, it is going to schedule a garbage collection, which will eventually happen. Also, the other thing to keep in mind is that garbage collection in a server application works a little bit differently than a desktop application. Garbage collection in server application, at least for .NET Core and .NET 5 applications, happens in background, and it is called background or server garbage collection. And in case of the garbage collection, there is a separate thread which is responsible for garbage collection during server garbage collection, and it continues to collect garbage along with other thread allocating memories. Whereas in case of desktop collection, when the garbage collection happens, the allocation threads are suspended. That's the only difference. So that's all I wanted to cover about garbage collection today. If you like this video, please give me a thumbs up. If you have any questions around the whole garbage collection process, please leave me a comment and I'll try to answer them. And if you're watching my channel for the first time and if you think you are going to get value out of my channel, please subscribe to my channel. And thanks so much for watching this video.